involved in the implementation of CLS and Chromium. And I guess people are interested in the algorithm and the performance optimizations we did, so I can share some details about that. So I guess the first thing to understand is we hook into the existing rendering pipeline to notice when an element has shifted. So the same code that updates element offsets for painting also notifies the layout shift tracker. You might think it would be the layout code, but it's actually the paint code because we care about the visual rect. Anyway, when we're done painting, we've accumulated this list of rects. And we added, anytime we noticed an element had shifted, we add its old rect and its new rect. So you can imagine a page with a lot of elements that could be a big list. And so CLS has to calculate a score. And the hard part, which is sort of algorithmically interesting, is to calculate the area of the union of those rects, which is this sort of region of arbitrary complexity. And our first attempt was n squared in the number of rects. Basically, every time we add a new rect, we had to compare its overlap with all of the previous rects. And this showed up in our perf alerts. So they said pages with lots of elements moving around are measurably slower because of this. We actually found two ways this could be fixed. The first was to snap the region to a grid. If you imagine sort of a coarse grid with lines 50 pixels apart overlaid on a page, then align each rect to that grid and sort of scale them down before you calculate the area. This sacrifices precision and potentially introduces a new way for browsers to diverge, which is, you could say it's an interop problem. We actually put into the spec that the user agent can make these kinds of trade-offs. So in my view, it would be perfectly okay to do this kind of thing. But we found a new way that's both fast and precise. It uses a data structure called a segment tree. So imagine your input rects and just look at the y-axis, get all the endpoints where any rect starts or ends. And the segment tree is like a balanced binary tree where the nodes are the intervals between those endpoints. And then finally, imagine a sweep line on the other axis. So we're sweeping from left to right. And at each X endpoint, we update that segment tree to reflect which parts of the sweep line are overlapping the region. And so we accumulate the area as we go. So each step, the segment tree tells us the total vertical overlap length, and we multiply by how far the sweep line has moved horizontally since the last endpoint. So the time cost for n rects is log n every time we update the segment tree, and we update once for each endpoint. So n log n overall to get area for a single animation frame. And the other half of CLS is move distance, but that's trivial because again, the paint code notices when an element has moved. So we just keep track of the biggest move that we've seen. If anyone feels like inspecting the Chromium code, the interesting bits are in this class called layout shift region. I haven't really studied the Mozilla or WebKit rendering architecture lately, but I would imagine a similar approach could be taken there. Or at the very least, I don't think there's anything inherent in the CLS spec or the web platform that makes this computationally intractable.
Well, thank you.
That's all I have.